Hey everyone, I know you're all working hard to get through these acid base, predict the direction type questions, and some of us are maybe not feeling like we get it quite as much as we'd like to. So I'm putting together this as a quick tutorial to kind of walk through the process step by step with you to help you understand what I'm asking and feel more confident about completing these problems on your own. So this is the type of format that you should be used to seeing by now. We'll have two things, a box for you to put some answers in, and a couple of question marks for our product structures. So these are the instructions that you will see in similar wording, and this is what I'm asking you to do. First things first, redraw your acid and base, show how the proton transfer occurs, and by that I mean with arrows. Next, you'll draw the products of the reaction. Then you'll add the correct arrow in the box based on either comparing benchmark pKa's or listing the factors and comparing them that way. And at the end, I will want you to choose the factor that makes the strongest acid stronger. So we'll come to what that means as we go through this example. So on this next slide, we have the exact same thing, just cleared out those instructions to give us a little bit more room to work. So before we even get into all of those different parts of the reaction, we have to know first which compound is our acid and which compound is our base. If you're not sure about this, go back and review the lectures where we talked about identifying acids and bases, different types of functional groups. You can also always refer to your pKa benchmarks here. So for these two molecules, what I'm seeing here is this kind of double bonded CO and then an OH functional group, which I've seen is pretty acidic, and nitrogen, which could be kind of acidic, but actually those are more often used as organic bases. So I'm going to go ahead and pre-label this compound as my acid and this compound as my base. Note they might not always be in that position, so you have to use your intuition. Sometimes acidic hydrogens might not be drawn in, and you may have to draw them in yourself. Then I'm asking you to redraw these compounds below, A for practice drawing, converting structures back and forth and practicing your drawing skills, but also so that you can draw out lone pair electrons or the bond to the most acidic hydrogen so that you can show with arrows how it gets transferred. So literally that is just recopy exactly what I gave you at the top. I'll try to draw it in my slightly messier handwriting to make it look like something that I wrote. There we go, by hand. Except I don't want to leave that H bond like that. I want to draw it out here because I'm going to have to break it. This is the proton here, I'll highlight in blue, that is going to get transferred. And then similarly for the nitrogen, I know that's the base, and I want to really highlight this lone pair of electrons because that is the thing that's going to allow us to do this proton transfer. So that's all I mean by redrawing our reactants. Next, we want to show how the proton transfer occurs with some arrows. So as we talked about before, you are going to learn a lot about arrows in organic chemistry, but for now, what we need to do is always go from the base to the acid. So here we go, from the base to the acidic proton. And we're going to pick it up using that lone pair of electrons. But hydrogen only likes to have one bond at a time. So that means that these two electrons here are going to have to move and they get pushed over onto our oxygen. Okay, so that's what we mean when we're looking for you to show us what happens during the proton transfer. These arrows illustrate the movement of electrons that facilitates the transfer of the proton. Then we want to move on to step 2, draw in the products of the reaction. Here, we just want to provide two structures that fill these kind of blanks in. You don't have to write them over top of those question marks. If you don't want to, you can just draw them down here, which is what I'm going to do. So the key to predicting the products of this type of reaction is to not overthink it. All you're doing is moving one proton. So even just to hit that point home really even harder, I'm going to literally just copy this. Now you may not be able to do this as easily if you're not working on a tablet, I understand that. But I'm just literally going to redraw exactly the same thing, but know that I broke this bond here from that oxygen to that hydrogen, and I made a new bond using these electrons to that hydrogen, right? So literally all we're doing is moving this proton over because it made a new bond with nitrogen using these electrons, which I will now erase. And we had these two red electrons here that used to be in a bond, but now they're just sitting on oxygen as a additional lone pair. Remember, there are two here. to begin with. So those are the products of our reaction, but we're not quite done predicting yet because something is wrong with these structures. Go back and refer to your formal charge chart that we walked through in one of the earlier lectures this semester to remind yourself of what bonding patterns look neutrally charged, positively charged, and negatively charged. Long story short, oxygen likes to have 2 bonds and 2 lone pairs to be neutral, as it does in our starting material. But when we give it more electrons, it takes on a negative charge. And therefore, the nitrogen must have a positive charge. Even if you don't feel comfortable with that pattern of bonding, you have to have the same amount of charge when you begin to when you end, right? Over here, we have a net 0 charge, nothing is charged. Over here, we have to have 1 negative to balance out 1 positive and maintain an overall net 0 charge. So now we've finished predicting our products and we are nearly halfway through this question. The third part is to decide which direction the reaction goes and put the correct arrow in the box. So now we should come back here and compare our acids to one another to decide which one is stronger. So I'm going to underline, actually let's go ahead and label over here. Our conjugate base comes from our acid, so that must be this. And our conjugate acid comes from our base, so that must be this. So we'll compare our first acid to our conjugate acid and then see which one has the lower of our baseline pKa values. Or again, if you prefer the factors and not memorizing pKa, that's totally fine too. The functional group that we talked about here, right, is one of our benchmarks. So that has a baseline pKa of around 5. And the positively charged nitrogen is on our chart there. That has a baseline value of about 10. So there's some rough pKa values for you. We can also start to look at the different factors that are at play in both of these molecules and decide which one has more factors that we like. I'm going to do this quickly and not write them all out just for the sake of keeping this video short. Our factors include elemental factors, right? So we would be comparing oxygen to nitrogen. We would also be comparing the hybridization of our atoms here. In both cases of the acids, they're sp3 hybridized, so that would be a tie. We would compare the ability for resonance to occur. And then finally, we would evaluate the availability of induction. So one of these compounds does have the availability to resonate because of this single double bond arrangement, whereas our conjugate acid does not have that ability. And neither has the ability to do induction because there are no fluorine or chlorine atoms present. So whichever way you choose to compare, what you will find is that these are relatively close in strength of acid. You can do your delta pKa analysis if you like. Remember that is products minus reactants. So our delta pKa is going to be on the order of 5. That's still within that window of equilibrating. So we will want to choose the equilibrium arrow and put that in our box for our final answer. Like so. And then the very last part is listing the factor that decides the reaction direction. So we didn't go over a whole lot of the elemental factors comparing oxygen to nitrogen here. So go ahead and practice that more on your own time if you need. But the one factor that I did point out was the factor of resonance. The fact that we have resonance available here in this acid, but we don't in this acid, makes our original acid, or this doubly bonded oxygen containing molecule, the much more acidic compound. Hence, this is again also reflected in its pKa value. So even though we are calling this in perfect equilibrium, it's really a little bit one-sided. We are saying that this side has the stronger acid. And that would predict our reaction direction if this was a lopsided equilibrium. So with that, I hope this video has been helpful. If you have more questions about the homework, please feel free to send me an email. I'll be checking intermittently tonight. Hopefully this will also help in your preparations for exam 1. I can't stress this enough. Chemistry is hard, and I want to help you out with it, even if we've been doing this virtually and asynchronously. So reach out with an email anytime, or send me a Canvas message, or stop by office hours. Good luck.